that's been sent into. So, okay. So now, why and how do we understand this phenomenon? And this was something which, okay. So now, the other idea with, or like, what it was put forward was that it's observation which kind of changes the way the photons are coming through the slits. So now this is again something against the realism which we kind of discussed, right? Which kind of we had an understanding from the what we call it the real world understanding, right? So if I have a photon which has been sent, and if I'm clearly following or I'm keeping track of where it is going, whether it's going to a slit on the top or it is going to a slit on the bottom, then I would end up seeing the pattern as if it is a particle and it has been accumulated here. But if I'm not observing, which means that if I'm switching off the information of where it is going through, then I would end up seeing a wave behavior. And this is something which kind of says my observation is altering the way the photon is traveling through the slits or electron is traveling through the slit. So this again, we can go back to what we call as uncertainty or particle wave duality nature. So when you are observing, you are kind of collapsing its wave packet at every point of time, and you are only capturing the particle behavior. When you are not observing, which means that you are letting the wave packet to behave like the wave and the amplitude split across the two slits, and you end up having an interference pattern. Okay, so this is something, a solid example which kind of came as a question to realism, which we all believed in, or which they all believed in at that point of time. So in summary, we can say that this is one of the experiments which first came, which kind of became very a standard model or example to explain the quantum theory or the wave particle duality nature. Knowing which part or slit the photon travels through forms a measurement. It is kind of treated as a measurement in a system. So measuring the photon collapses the wave packet, and the particle behavior is observed, and the interference pattern fails to form. So we don't see any wave behavior, we only see a particle behavior. So when you're not observing, so if no information exists to link photon to a specific part, then the wave behavior resumes and interference pattern is observed. So now this is something which kind of said that there is a deviation from our standard understanding that there is a both wave and particle duality. The other important experiment which kind of really set quantum physics into what we call as a mainstream is the Stern-Gerlach experiment. When I say real, it means that there was also an experimental observation which clearly quantified the quantum behavior of the spins, right? So Stern-Gerlach proposed the experiment in 1921, and in 1922 he performed this. What it says is that you have, I think they have used the silver atoms from the oven, and when you send a silver atoms or which have spin orientation in it, and then you have a gradient magnetic field. I mean, you avoid an uniform magnetic field, you create a gradient magnetic field. When you send them, you would end up seeing atoms deviating to two directions, and then you would see them spot in two different spots exactly at some particular length. So you will not see a continuously distributed atoms across the screen. So this is the experimental result you observe. But in principle, from the what we call as a realism understanding, it should have behaved like this. What is at the backside, the classical prediction would say that atoms would have spread all across the whole screen, but we would end up seeing quantized with just like spin up or at h bar, what we call, or spin down at two different positions. These Stern-Gerlach experiment kind of gave an exact picture of quantization of spins, and then you will only see them at one intermediate level. So this is another example which kind of experiment which also posed a challenge or a question realism which exists. So a simple example to see how this challenges is this. I will just go step by step example, and this is quite useful for us to see how entanglement comes to the picture. This is the next level of it, right? So in this setup, we have a source. I have a magnetic field which are inhomogeneous, and then as a result of the magnetic field, we end up having this for quantized split of atoms. You know? So this whole unit we would treat it as a magnetic field in z-axis, right? So I have a O1 from which atoms are sent, and then I have a magnetic field, inhomogeneous magnetic field, and then we would end up having two beams coming out with plus H and minus H, or we can say that the two quantized beams would come out of it. Now, if I block one of the beams from the two quantized beams, then it means that I'm only having a spin-up atoms which has gone through the second one, and I again do the same inhomogeneous magnetic field, and nothing, I would only see a deviation in the up direction, and then I would not see anything coming in the because I only preserved the spin-up atoms. I don't see anything in the output, right? So this is kind of expected. It's kind of accepting the realism. So if I filtered out one of the spins and only spin-up is going through, which means that exists and it's accepted. Now, if I am changing the orientation of the magnetic field, which means that in the previous slide, I showed that the magnetic field is along that direction. And if I rotate it in the next direction, means completely twist it, then I would have again two beams in x direction. So what were two beams in z direction, now I also get two beams in x direction. So that is also understandable because you have kind of splitting happening in the x direction. We end up having two beams. So then if I'm blocking one of the x directions beams and I send again along the z direction a magnetic deviation, in principle, I've already filtered out here. Like if I see in the first scheme, I've already filtered out only plus z direction beam of atoms. And then I've now got two of x direction, and I've also filtered out one of the x direction beam also, which means in principle, I should not have a z minus beam going in at all. But suddenly I would have z minus beam also reappearing in our measurement output. And this was a real experiment which was done, and then they got the output and they were calculated. So knowledge of x orientation, when the moment I'm going into to seek the information of what is the x orientation, I'm destroying the knowledge of the z orientation of the momentum, or what we call the spin direction. So this is again kind of a contradiction to the realism which we understood, right? So to understand what is the realism, I just have a small analogy with the classical one. I'm always hesitant to give a comparison of a quantum system with the classical one, but it's still, I think this is not a very bad one, and we can take it with at least it will give us an idea of what we should expect if it's a classical one. So if I have a classical object and I have two entities here, because here we took z and x direction, are the two directions of measuring the splitting of atoms, or direction of the magnetic moments, right? So the classical analogy, I can take color and shape of an object. I have some closed system, or like in a closed room where I have an object. The object can take two shapes and it can have two colors, right? I will again treat as blue and green, or like some two colors, and have two shapes. So now, if it will be a dark room, I will not have any information of the color. I can't see the color. In the dark room, if I just want to identify, just pick and see what shape it is, right? I'll be given either Z or like triangle or rectangular shape, right? So now the whole setup will go, right? So it means that if I'm just looking for a shape, and if I pick, I'm going to get a triangle shape. It's just like doing a Z rotation, Z measurement on it. So I'm doing a classical measurement here. I will identify that it is a triangle. Now, again, just like the way we said, because I've already fixed it is triangle, and a number of times I observe it or I see it, it will still always be triangle. Nothing is going to happen to it. But then I'll take that triangle, or triangle, and I also want to identify. I'll turn on the light and I want to see what color that object is. Either it should have been green, or I was told in advance that it will be green or it will be red. So, but the moment I turn it on and I see the color, then it is red. So now, which means that I've already identified the shape of it, I've identified the color of it. Now, if I try, just like the way I did here, Z and X and Z, if I try to change and see what, whether again do switch off a light and look at the shape, nothing changes. It's like it would be foolish to again go and do an experiment, because for me, my classical realism, or the way I understand the world, kind of that nothing is going to change. I've already identified my color and I've already identified my shape. So why should I go and do that? But in contrast, what we see in quantum mechanical systems like atoms and the spin orientation is that the moment, again, is the two properties of the same object. It's color and shape here. It is the orientation, or what we call in the Z and X direction, right? Orientation of the spin in Z and X direction. But here, knowledge of X orientation destroys the knowledge of Z orientation. But here, knowledge of current, color does not do anything to the knowledge of shape, and they are very independent to each other. So this is the first thing we know. Again, like we mentioned about the the wave and particle nature, where they are together. The moment I'm looking at the particle behavior, I'm destroying its wave behavior. When I'm looking at wave, I'm destroying its particle nature. So the same way it happens with electrons, or what we call an atom's spin. So these two quantum mechanical systems do question realism, or the experimental observations question the realism which we have as an understanding from the classical scenario. So, which really puzzled Einstein for a long time. He could not accept that quantum mechanics can be so strange, and he could not accept that something really unknown thing is happening. So he had made a statement, says like this: I like to think that the moon is there even if I'm looking at it or not looking at it, right? So even if I'm not looking at it, the moon is always there. So irrespective of it, he didn't wanted anything to change. So, so for him, this was a big puzzle, and he always had, he could not believe that quantum mechanics, or the way we understood quantum mechanical systems, was complete. So he thought there was some loopholes in our understanding. So there is another part. I mean, I only looked at the realism here, but locality is another important aspect, which also was questioned by quantum mechanics. Locality, which we understood from the classical scenario, which says that causes must travel through space-time at the speed of light or slower. So nothing can travel faster than light, and that's as simple as this. And we are all familiar with the special theory of relativity and how speed of light comes as a bond. So here, for example, we can think of two people, Alice and Bob, right? And then Alice and Bob have two objects or two shapes with them, right? You have triangle or a circle and then different colors. So they are completely isolated. There's no communication between them, and they don't have any form of interaction, right? So we assume that they are completely isolated and there's nothing between. So now, when can locality be questioned? And that is what is the idea. What about locality and when it can be questioned? If Alice and Bob have a strategy such that they can always pick one of the below configuration without exchanging any information, like I've given the configuration below. We'll look into that. If there is some way that they have a strategy where they have some correlated result coming out from their measurement, then which means that there is a violation of locality. That means that there is some superluminal propagation of causal influence, which means that, again, to put it in more simple words, there is some information which has been traveled between Alice and Bob at the speed greater than light, right? So, or it can be an instantaneous transfer of information from Alice and Bob. But if we make sure that they are, even after making sure that they are isolated in two different rooms, if by some way they can get some output like this, like for example, if Alice measures triangle, Bob should have also got a result as triangle. Or if Alice measures circle, Bob should also measure circle. This is one possible possibility configuration. Whenever Alice picks that circle is my choice, then Bob should have automatically picked circle. Whenever Alice picks triangle as his choice, then Bob should automatically pick triangle. Or it can be another configuration where if Alice picks triangle, Bob should always pick circle. If Bob always picks triangle, then Alice should always pick circle. So these are kind of configuration. If they have some strategy to do this, then the locality is also questioned. So now I'm just giving this as a classical scenario. In classical world, this is not going to happen, right? But quantum mechanics do question this locality, which we understood. Just again, I'm simply revisiting why such this kind of question came in, why locality came in, and why people thought that quantum mechanics may seem to violate this, and something should be done to fix the whole understanding around that concept or idea, right? So now from 1901 to 1920, 30, various interpretation came in, and then there was a settlement to Copenhagen interpretation, which kind of said that, at least this is just a rough postulate of it, where a system can be completely, or like, if you take any quantum mechanical system, we can always describe them with a wave function, right? Because that is the way dynamics goes in. Wave functions capture superposition and interference. Like I mentioned in the beginning, when we had double slit experiment, you can have photon which can be in superposition along the two slits, and then they interfere before they fall on the surface or the screen where we are measuring, right? So, and what Copenhagen interpretation said, that you can always describe them completely using wave function, which means that you can describe the system. Not beyond that, let's come to the next one, right? And then is probability of finding the particle at any given point, or it can be any state, right? I mentioned you can have spin degrees of freedom, so it can be at given point, or it can be a spin or whatever degrees of freedom we are taking. When measured, is proportional to the square of the particle's wave function at that point. So this kind of says that your Bond rule says that the probability of finding a particle is the square of the amplitude of the wave function. So that's something which we have practiced, and that's what we have been doing from the day we started learning quantum mechanics. We write wave functions, and then there is the square of that amplitudes or the wave function, which kind of gives it a probability. And the other important point, the measurement collapses to one of the basis states. So it means that you can have, like we mentioned, there was an interference pattern which came, but that interference pattern is not at one-time experiment, right? You keep on sending hundreds of photons, and after a long time, you end up measuring them. Which means each time I'm measuring, it is collapsing to one or the other place. The interference pattern I'm seeing is a collective observation of thousands of photons which has been sent. One photon collapsed at one position, and the other photon collapsed at some other position due to measurement. So the collapse of wave packet is something which is really the one which is destroying the information of all other states, which could have been like it was like in the first statement it said it can be completely described by wave function, which means that it keeps the information of superposition, it keeps the information of interference which is happening in the system, everything. But the moment I'm measuring, all that information is lost, and only at one particular basis or at one particular point, there is a collapse of the wave packet. So this is all fine when we are looking at a wave packet of single system or single particle. The big question came in was the composite system. How do we treat interacting systems together? Like I might take two photons together, I would take two atoms together, and then they are to be described. And the way Copenhagen interpretation started giving a mathematical frameworks to quantum theory was Hilbert space language, where we have a vector representation of them. So when we have an Hilbert space language and when we give a vector representation, the composite systems are always described as tensor products. The moment we start looking at tensor products, we do end up having some strange states, which kind of is what we call the questioning of what we call the locality issues, right? So it's kind of brings in entanglement into the picture. The moment we start looking at extending what we know from the first 3 points for the single wave function we studied, and the moment we are taking up into composite systems, we are into an entangled state kind of picture. So what it looks like. So you don't have to worry too much about the mathematical description or like expressions. They're very simple vector representation. If I take two composite systems, and then it's a tensor product, probably with all the basic maths, everybody would be familiar with this tensor product representation. I have system A, I have system B, and then I can put them combined together as a tensor product. So when we say vector, which means that there is a 1-0 representation, 0-1 representation. I'm just giving it as a Dirac notation, but it can simply be treated as spin up, spin down. Or if somebody who are familiar with photonic language, we say horizontal, vertical polarization. I can treat horizontal and vertical polarization as the two different possibilities, and I can give them a quantum state representation. Because they can be in superposition, both particle A or like, something system A or a system B can independently be in superposition. Okay, this is an independent representation. There is no interactions between them. They are two independent representations. When I combine them together, like, writing a combined state or a wave function for that particular two composite system is just a multiplication of them in a tensor representation, and they all look like 0, 0, 0, 1. These are four possibilities, right? There's nothing special. But because of alpha, beta, these are wave functions, which means that they have complex variables, the vector in the vector representation. We can have some configurations where you can have subtractions and addition. That's what when you said there can be interference between them. So alpha could, gamma could have been same value as beta with minus sign, or some other values, right? Various strange values could have been there. But some amplitudes could be zero. The moment you have some amplitude zero, then we can have a state something like this. And this is also a mathematically valid quantum state. If you have a state like this, which means that I'm beginning with some system which are separate, right? There is no kind of any interactions between them. But if by some mechanism I end up having a state like this from the two composite system, then they will not be separable, which means that I can't independently describe A and B. So it means that I need to collectively have some observations between A and B. So in fact, before we go detail, in detail into entanglement itself, in this expression itself, I can give you some idea of what really entanglement means here. It means when we said the wave packet collapses, it doesn't matter whether I'm taking a single system or I'm taking a composite system or complex many body systems. If I'm writing them all as a summation of various possible outputs, then measurement collapses to just one of them with certain probability. If it is this expression, measurement will collapse to just one of them, right? Not all the four. So if measurement collapses to this state, which means if Alice is in state A, then 0, then Bob is also in state 0. Which means that if they are spatially separated, if Alice gets 0, then Alice knows that Bob has also got 0, right? And if Alice measures state 1, then Alice will know that Bob has also got state 1. This, if you can actually see here, this is the case here, as mentioning. If Alice has triangle, then Bob also has triangle. If Alice has a circle, Bob also has circle, right? And that kind of scenario comes here, which is a question on a locality idea, where because Alice and Bob, there is no condition here. There in this mathematical construction of quantum theory, the way the Copenhagen interpretation I put in, there's no other feature which is coming in here. Right? You're just writing them as the summations, and then you see the collapse itself says that. It doesn't say that they have to be physically somewhere at close distance or something. They can be separated, spatially separated, right? So if they can be spatially separated, then there is an instantaneous information of state B on Alice's side, because Alice would get to know what's happening. So this is something which kind of puzzled Einstein again when it comes to composite system. So these are some examples of the Bell state. Like I've written here, which we call as Bell state. I can simply say that these are examples of entangled states, right? It can be in this configuration. We can have a source. It can send 2 photons, or it can send 2 atoms to 2 different bodies A and B. If there is some way, we are not even addressed that how can you actually arrive at the state, but let's say there is some mechanism where you can generate some state like this and send it to 2 spatially separated points, Alice and Bob, and the measurement on Alice's side will instantaneously reveal what Bob has got. So it can be in configuration, various configurations. If it's photon, it can be polarization of photons. It can be in this configuration or in this configuration. And all of this can't be separated as independent or individual systems. So, but does this exist, or can somebody experimentally look at it, was all a question. But what Einstein did was Einstein, Podolsky, and Rosen together that put up it, but Einstein could not accept this as something which is possible quantum mechanics, or in physics, in science itself, general nature does not allow something like this to happen. So it kind of called this as, can quantum mechanical description of physical reality be considered as complete, which means that something is missing. So they called hidden variable might exist, which means that in this expression, the way we have evolved, there is some parameters or some variables which are not been able to identify and bring it into this expression, which will give us answer for this instantaneous information exchange. That is, the causality is not violated, that nothing is transferred or nothing, no information is exchanged at a speed faster than light. So here, I kind of makes a statement that in a quantum mechanics, in quantum mechanics, in the case of two physical quantities described by non-commuting operators, the knowledge of one precludes the knowledge of the other. Then either one, the description of reality given by the wave function in quantum mechanics is not complete, or these two quantities cannot have simultaneous reality. So this is something which kind of puts it, and then they start giving arguments for why that there might be some hidden variable, and one has to find out what it is, and all of those details will go in this paper. So I think the debate continued for some time, and there was various other approaches people were trying to look at, because it's not even easy to think of experimentally having it, and people were also coming up with various possible interpretations of quantum mechanics to see if that can fix. But Bell had a very different approach to it. Like many of the sciences we do, or like people try to look at in the previous century, was if we can't find out directly that this is the observed, we can't establish something with direct observation, we can also begin with some hypothesis and try to see if we can contradict it. If we can't contradict it, then we can establish that what our hypothesis is correct, right? You can establish a hypothesis itself as an observation, right, based on our attempts to contradict them. So Bell came up with some example where, or like some experimental proposal where he said, if we can do these experiments and then verify, if it meets certain conditions, then we can say that quantum theory is complete. If it does not meet certain conditions, then we can say quantum theory probably is incomplete, right? So what is that condition? So this is a simple, again, a classical example. What he said, again, it came to the idea of start with an hypothesis. Any realism, anything which has to do with locality, or any realism and locality together, should follow certain conditions, right? Which means that if we do some experiment, we should get certain output. So this is purely a classical way of looking at it. So there is a source. The source is sending some information or some quantum. It may not be quantum mechanical, right? Just it can be a value, right? X is equal to 0 or 1 is sent to A, or Y is equal to 0 or is sent to Bob. So now, depending on Alice and Bob can have any kind of protocols for them. Like Alice can actually decide if she gets X as 0, she will call it as +1, or she can also decide that if she gets X, she will call it as -1. Same way for Bob. So it means that they can choose whatever values as +1 or -1. It means this is the value they are going to assign. If Alice measures 0, she can assign +1. Or if Alice measures 1, she will assign -1. Or she can do another way. Same way Bob can do. Like Bob can also choose a configuration whichever he wants, right? So this is classical possibility. So which means that source is sending X 0 or 1 to Alice, and source is sending 0 or 1 to Bob, and there is no control on where it is. They are just sending some zeros and ones, and Alice and Bob are measuring 0 or 1. The moment looking at the output, they get 0 or 1, they are going to assign plus or -1. So classically, or from the way we understand the measurement from local realism, or what we call from local realism, we are going to get, for one configuration, for example, if Alice is going to take 0 as plus and 1 as -1, so we can always put in the values here, right? This will be +1, and this will also be +1, and that will be like, totally together it will be +1, this will be -1, and this will be -1, and this will be +1, right? It can give some value 0. So, but choosing various alternative configurations, the maximum we can go up to is the +2 and -2 values. You can get some range of values between these two configurations. That is a classical realism, which kind of comes in. So what Bell suggested, this is the simplest form of putting what Bell explained. But what he said was, if there is any quantum source for which we repeat the similar kind of experiment, and if we see that there is a violation of, or if we get something more than 2 value, then which means that there is a non-locality effect, which is in quantum mechanical system. Or if it all falls into between 2 and 1, then something is missing in the way we understand the quantum. So, but this was the hypothesis or the way the experimental proposal which he had proposed, and people didn't think that you can actually do this experiments and verify using a quantum mechanical systems, right? But a more refined version came to verify this experiment. This was by Closser and his group. Closser and his collaborators, CHSH call. I'll bring in them later on in detail. But you can have some configurations. For example, you can have a photon. This was the fine-tuned experiments, which are sent, created in some uniform or like some special configuration of HH plus VB, and they're sent across 2 different locations, Alice and Bob. And Alice will have some different measurement approaches, and Bob will have different measurement approaches depending on what polarization they are measuring. You can have some coincidence values, right? So you don't have to look at all detail, but just the correlation between them, +1 and minus sign is what we can think of. And if we are kind of assigning those values, then we would end up having always, if it's the classical behavior, or if there is some local realism exists, then this will always be less than 1. But the moment if we have something which is a violation of or what we call a non-local effect in the system, then it will be greater than 2, and the maximum one can achieve for Bell state. Like for example, I gave this example. These are the possible Bell state, right? If you are sending, preparing a state in the Bell's configuration, Bell state configuration, and you're sending them across 2, then you would end up having something like this. The maximum value will be greater than 2. 2 root 2 was the kind of defined form of doing an experiment, or like adopting the Bell's non-locality into a real experimental scenario. So this was done by Closser, and then the first experiment. In fact, Closser was not somebody who really wanted to show the violation of Bell's inequality and establish non-locality. For him, he strongly thought that if he does an experiment, he can actually get against this, right? He can actually satisfy the locality realm. He wanted to prove that quantum mechanics is wrong or something is seriously incomplete with it, right? So he went to Feynman asking that you suggest, or like to get his feedback, and he did propose that he wants to do this experiment and then prove that the quantum mechanism. But Feynman didn't wanted to rely on the Bell's experiment or suggested experiment to believe in quantum mechanics. He strongly believed that quantum mechanics is reality, and there are various other ways to believe that everything is correct in it. And he kind of actually, I think recently Closser did say in one of the interviews after he got the prize that Feynman had actually sent him from his office, just get away or get out of my office. I don't think it's a experiment which you have to go and do. But somehow Closser strongly believed that he could probably go ahead and then show that there can't be violation, or there can't be non-locality. And I did perform experiment, but somehow what he got was a validity, or like kind of, or like what he could show the violation of Bell's inequality, which means that the S value was greater than 2 in the experiment you performed. It was a very you can imagine that it is in 1969 he first proposed CHSS, they kind of came up with this description which I gave here, how you can have a correlation of the possibilities and then calculate the non-locality effects of that. So, but in 1972, the experiment was done along with the student Fedman, but they kind of, this is the experimental setup. where they had calcium atoms which could emit entangled photons, and they were spatially separated up to, I think, roughly about 10 meters, sorry, 10 feet. When they were spatially separated up to 10 feet, they had some filters to see the orientations of them or the polarizations, and then they measured, like the way kind of described here, the correlation of measuring the polarization, and then they could show that there is a violation of Bell's inequality, which means that there is clearly a non-local effect between the two photons, which means that you can have an instantaneous information exchange between them without having anything really physically transferred. So it was not a violation of causality. I'll come to that later on, but it was still could show non-local effect very clearly. But this experiment was not was something which could have a lot of errors in the way the filters were placed. And since it's a very small number which is verified, some people even kind of had doubts that it can be an experimental error. No, or having a value greater than 2 might be an experimental error. And it went on further refinement. And one of the refinement was by Alan Aspects. And what he did was kind of, instead of going with this heavy experimental setup like this, which had calcium atoms, so it kind of used a smarter way of generating entangled photons using crystals, and then setup was more simpler. And there was, they used different filtering techniques. So here, the two entangled photons were sent, and then you could have orientations to filter out different polarizations effectively into multiple paths, and then you could do the experiment. And this is an experimental setup which kind of eliminated the errors which could have come from the filters, and it really used a well-defined high-rate single photons, which were entangled photons which were emitted. So the photon numbers were high, and then the filters were very properly aligned to clearly establish that something was very clearly greater than 2, close to something like that. So this was, again, the scheme was proposed in 1976. Kind of the idea of how it can be done. So it really took them 5 to 6 years to complete experiments, and it was published in 1982. So it kind of fixed the loopholes in the way the measurements were performed in the system. So it also established that there can be 2 photons which can be spatially separated, and without even having any communication, the measurement on one photon will reveal the information of what could have been the state on another photon. So that kind of established. So now there were a lot of questions came in of what we call non-existence of free will. So that the systems might all have been controlled by something much more superior than all of these things. It means that this item which has been emitted itself might have some information that's been communicated, and we don't know them, which kind of said that the locality loophole kind of thing. But it was fixed in 2015, where I said the measurement approaches, when we said in the previous, here we were telling that you have to choose align +1 or minus, assign +1 or -1 depending on the way X and Y are coming in. So here what they did was they took the signals from the faraway galaxies, right? The whole signal were taken from galaxies to control the filter orientation, right? It was randomly what orientation you need to send, like to which detectors you have to send. This was decided not by any man-controlled devices or anything in a laboratory setting. So these were coming from 2 different galaxies which are separated by light arrays. So taking the light signals from them, the orientations of the filters were so, which may kind of said that the way you are calculating the correlations didn't have any human intervention in the systems, and something was coming from. So this kind of fixed the non-locality loophole, or what we call the information is coming in. So it's very well established that there is clearly an entanglement which are measured between the 2 photons which is being generated in that. But of course, this was one extended part, but Zallinger and group did a lot of experiments. So Aspects and the Clauser experiments, all those 2 established Bell's inequality in different with further refinements. Salinger experiment fixed the loophole, but I think the prize was also given telling that it's not just for, entanglement or the violation of Bell's inequality experiment, but to also see it applications in a larger or for practical application in information processing. It can be in computation, communications, or various other systems. So another experiment which has been cited in the Nobel award, this is that they did do they did have an entanglement swapping experiments or even teleportation experiments. So instead of just having one entangled photons sent across the space, they could even have two entangled pairs. They don't have any kind of interaction between them, and then they could bring in an interaction between part of those entangled pairs, and they could make these two parts entangled, right? These two photons entangled, 1 and 4. So 1 and 4 had no interaction, they were not entangled before, but just by making 2 and 3 entangled in the setup, they could make 1 and 4 entangled. So this kind of said that you can actually engineer entangled state and use it as the way for exchange of instantaneous information. So this instantaneous information exchange has a very big implications in communication, because my talking to you all, or the communications between two different countries via satellites, they are all bounded by speed of light, and we do have you can have somebody intercepting the information, somebody hacking all our information. All that is needed is a very efficient attack protocols or algorithms for them to hack into our systems and look at it. If we have entanglement as resource, and if the information can be exchanged instantaneously, then the scope or for any hacking can be completely ruled out. And that was one of the big motivation for quantum communications to become one of the established areas. I mean, a lot of development is happening across and around. So this is the three. In fact, I think this is the main core for which they've been given Nobel Prize. But I would also see, how we get. It's not okay. It may look nice to see that you can get entangled photons, and one can show there can be an instantaneous information exchange between two of them. They can be spatially separated by long distances. People have done experiments of hundreds of kilometers, and they have verified entanglement between two different points in Europe, mainly in Geneva and Europe, or even Austria, experimental setups. But it's not always very easy to get entangled photons. Experimental procedures are still very difficult, and still one of the most established one, which Alan Aspect's experiment came, was you can, this is standard approach, which we call a spontaneous parametric down conversion approach, where you send some laser light of some particular frequency, and then you send it to a crystal. The crystal has atoms, and then they do interact with them. When they interact, there is an absorption, if I send some particular frequency, the crystal observes the photons, and while it is emitting back to come back to ground state, rather than coming or emitting one photon, it will have a stable intermediate state for which it first de-excites and then it de-excites again, which means that it splits into two photons of lower energy, and then two photons are emitted. Now the crystals have certain orientations and certain behavior, the way they de-excite. So we can have configurations where omega-1 will be H and omega-2 will be V polarization. Or we can have, one can work out more complicated configurations of crystals and how they emit and what frequencies they can give depending on various other experimental setups. And the momentum conservation should be there, right? Because two photons are emitted low energy. So what usually happens in the experiment is like this: you have photons which splits into two with lower energy, and momentum has to be conserved. The way they come is like this in two cones is one of the configurations, right? So when millions of photons enter the crystal, 1 in a million, or actually one less than that, would end up getting down converted, rest just pass through getting wasted. Nothing happens to them. In 1 in a million, when they get converted, we have this overlap region where you don't know whether the photon is coming from this cone, because one cone is coming, you are having horizontal polarization, the other cone you are having the vertical polarization. So at this point, overlap region, there is a possibility of photon coming from both the cones, right? Which means that because of momentum conservation, because of two photons coming from the absorption and emission, which means that one photon, if H comes here, it means that the V would be coming on the other side. If V is coming here, H is coming on this side. The rest would all be H photon or V photon. So one has to carefully tap only these two regions and then ignore the rest of them by filtering off or like putting some mask. And these are the entangled source for us. So this is an image from our lab in ISE where we generate entangled photons of some of our experiment. So these are the 2 points overlap regions where we get H and V polarizations, and we only take photons from these points, and they will be the one who will be entangled to do experiments. So it will like we don't know whether H will be here or V will be here, but with whatever it will be of this state. If one we measure is H, the other will instantaneously be V. If the measurement, if first one is V, the other one will be H. So as I said, we can have different kinds of crystals where instead of having this configuration, we can have HH plus VV also, right? And this is also the way we kind of, we can generate single photons by just keeping track of one of them. And many of experiments with quantum information and computing require single or entangled source. So I think I'm already reached the time limit. So I'll quickly, because I think entanglement, we can't just stop with defining Bell's inequality. There's a huge applications which has been lined up. I'll quickly run in 2 minutes. Um, People have used these entangled photons to do instantaneous communication. Two photons are entangled and sent spatially to separate locations. And then you have exchanged information between them, the instantaneous information. There has been classical communication channels. I'm not going to describe the whole protocol, but this has been the theoretical proposal was in 91, in the year 1991, but experimentally people have did it after a few years in 2004. But then various improvisations have been done and people have been exchanged. So one of the improvement is this, where in the year 2001, there was an original image which using Alice and Bob's keys, using the entangled photons, the keys of Alice and Bob were created, and this image was added with the key. So the image was encrypted and it was exchanged between the distance of 150 kilometers using the one of the European Space Agency's observatory. So it was a very successful experiment. And later on, I think in 2 years back, 2018 and 19, the Chinese group, Chinese researchers in collaboration with Vienna group, they have been able to exchange the similar way entangled photon between China and Vienna using satellites. So entangled photons were generated on the satellite and they were sent to two different locations, thousands of kilometers away, and very efficiently they could exchange some information between the two locations, right? And this is a recent experiments which again use photons, and it does have a complicated. We only looked at 1 degrees of freedom polarization entanglement, or might be just two photons being entangled. But these days across the world, entanglement have been done in various degrees. Using different degrees of freedom of photon and multiple composite systems, multi-parted entanglement are something which people are working on. But they may not have all have been the ones which you can spatially separate and control them, but on a smaller time scale or on a smaller space scale, a good experiments have been demonstrated. And this is one of the optical model where recently, I would call it as a good experimental setup where they have generated some 70, there is 76 photons to demonstrate some computational process, so which no classical computers could do. And this may not be an ideal universal quantum computer, but the experiment does say that you have a very good beginning and probably some things can be done. Again, it's not specific to photon, though the price has been given to photon, but entanglement is a resource everywhere now. Superconducting qubits, which IBM and Google are working on. This is Google's one, where they have 53 qubit processor, and each qubit is like one photon, or what we were talking about, one quantum system. When you have multi qubits, how you engineer and and handle the composite system, right? Multiple systems together would be like multiple qubits, what we call. I mean, just as the language of quantum states of 2 degrees of freedom, we call qubit in quantum information computing. And when we combine them together, we can create complicated entangled state, and whole computation is done using such kind of entangled state. So this has been like recent demonstration again. They could do some operations which no classical computers could do, and it did have some weak entangled systems or like states created in that setup. Another interesting things which with entanglement we could see is that even in real life there are some dynamics which happens when you are looking at. Of course, when we measure them and we look at them, they're all in macroscopic scale. But when the dynamics is happening, or when some molecules are being formed, or some interactions are happening, there are some small quantum coherence which is happening, which means that there will be some weak entanglement between them, and that is what is leading to some complication. This is an example of one of the photosynthesis processes in a complex where light enters one of the states and then it takes multiple parts and goes into the reactor center. It's very efficient photosynthesis process, right? No laboratory setups. I know we don't have very good efficient solar cells, but nature do have efficient way to do photosynthesis. So this one example was one of the motivations for people to look at this subject was there is an algae in the sea, which is 5 kilometers below at the depth. One photons enter once in 2 days, but it efficiently converts into an energy. So there has been some explanations to say that there is some weak entanglement between the way the photons chooses the right path and efficiently converts into energy. And though they are very small scale and then they are still there, but entanglement is still has some important role to play in some of these dynamics. I think I would stop at this point and take some questions. Thank
you,
you,
Professor Chandru, for taking us through from the foundation or from the basics to the very end or forthcoming or very interesting topic. And now the floor is open. You can also post your questions in the chat box. I can read it for you. You can also unmute, and if you would like to ask the questions, I will give the permission to everyone so that you can unmute and you can ask questions directly.
So I think there is one question here by Krishna Kumar. Is it possible to observe quantum entanglement effect between identical physical objects if exist here in our Earth and other celestial bodies? So as I said, it's very difficult question, and probably I strongly, I personally don't think it will be very easy to answer this question, and might even not be very easy to do experiments or demonstrate entanglement between some very highly celestially subjected bodies or objects. But of course, one can have entanglement between the non-interacting. For example, there is a whole program CERN is starting, and then we also have tried to look at some of these neutrinos or some of these high energy particles which have been coming, which they're available, which is coming from somewhere from space, to see if there are some entanglement. And we do see that there is some entanglement dynamics in them. Particularly, one of the theoretical studies we looked at was neutron oscillation between the flavor change which happens between one of them to the other. And there is a signature of entanglement between them. And the entanglement, if we use entanglement and model them, we can clearly see the role there. But macroscopic celestial bodies are in a real world, in a macroscopic scale, can we see the kind of entanglement we are talking about or measure them? I doubt it's possible, just because the environment interaction or the way we look at, when I mentioned about some chemical complexes, or when we see how difficult it is to generate entangled states in lab, we see that environment effect plays a very strong role in destroying them as quickly as possible. It's only some, like, I said, non-interacting high energy particles, right? They don't interact, and they're just like, the robots. Photons are so nice because photons don't interact. Various other microscopic objects, they interact, then they decoil very quickly and they lose entanglement. So macroscopic objects, I doubt it will be possible in the near term to identify, to get any entanglement. but high energy particles probably one can measure.
Thank you, sir.
Any other person? You can unmute and you can ask the question. If you have any difficulty in unmuting, I can help you. You can raise your hands also. Otherwise, the reaction button is there. You can do the. Subramaniam, he wanted to ask some question.
Yeah.
Others? When we take a light particle, it basically it has the wave nature or in a particle nature. So when you are doing an entanglement, which part of the wave nature or particle nature which will be
when we are generating again, when entangled states are generated, it will still be the wave function, right? It will have the wave behavior which is causing it entanglement, right? So it's not okay. We are not separating out either particle or wave nature. It is exactly the way both exist, unless we are making a measurement. So measurement reveals us that okay, this was entangled. If repeated measurements, we say that okay, there is an entanglement. But I don't. I mean, you can't credit it just to a wave behavior or particle behavior. It's actually a collective. It's a wave function representation, I would say. Entangled state is still a wave function representation.
When you write in the initial talk stage of your talk, you said that is x direction and y direction and z direction. You have completely blocked one of the propagation directions. But how do you feel that how it is leaking into the other directions?
Okay, so it's not. We don't call it as leaking. What happens is that the moment you are when you have a wave function, when you have some spin, or like even if I'm looking at a polarization, right? So the moment I am measuring, it has collapsed there, and when the wave is regenerated, it is what we call reconfiguring itself and retrieving its information. So it's not like there's a leakage. I don't see it as a leakage. It's just because there is a superposition states all the time. I don't know whether I could answer you in a more reasonable way. What other way I can put it?
Can you able to the participants, whether they could able to unmute themselves? You can try it now, please. Krishna Kumar wanted to ask another question, I think.
Sir.
Yeah.
Could you hear me, voice, sir?
Yes, we can hear you.
Sir, we have different types of electrons now. So whether all electrons in atoms or in materials are entangled, sir?
No, even different kinds of electrons. So we have just electrons or electrons. But
yes, suppose, for example, we can take carbon or.
Okay. So you mean atoms? So
yes.
What? Okay, I understand what your question is. So this is a very when I mentioned about FMO, one of the chemical complex examples we looked at, or when we look at the way molecules are formed or the way atoms are formed, when they are interacting, there can be some entanglement which is causing them to form certain molecules. But most of the time, when we look at them, they do remain in the ground state, which means that they are most of the time it's a collapsed wave function, right? When we said I have a wave function, it's a superposition of all possibilities, right? Okay. So most of the time they are collapsed and they're more like a classical object. But if there are some interactions which are happening, and if there are some reactions which are happening, if there is some dynamics which is happening, then there can be some possibility of entanglement. So in fact, we did look at one of my student. I think he's also probably in the audience, or Pratik also tried to look at dynamics of electrons in aromatic hydrocarbons, where you had electrons hopping from one of the carbon atom to the other one, and it was creating that hexagonal structure, right? So we could see some kind of quantum behavior, and whenever we have some kind of interference or superposition in position space, you do have some different form of entanglement. So entanglement is not exactly like the way polarizations we kind of talk. They can be entangled in space, degrees of freedom. They can be entangled in time, delay degrees of freedom, or they can be entangled in polarization degree of freedom. They can be entangled in momentum. They can be entangled in energy degree of freedom. So people have looked at entanglement in various degrees of freedom. So they do exist, but it's not very easy to measure and quantify them. And till now, last few years, it is the photon which one can easily generate and model. Probably next few years, next 5 to 10 years, an academic interest is getting in that direction, where people would be able to look at entanglement in various other. Few years back, there was a big interest in seeing entanglement and quantum correlations in biological sample systems, and there was not a big success because the environment, we could not see any correlations, or people could not see correlations in most of them. There were very few examples, and it didn't take a backseat because lack of experimental, one sometimes for this field, you also need some experiments to support your theoretical predictions. Right? And now the experiments are improving. Might be it will be revisited.
Sir, and one more thing, sir.
Yeah.
In our universe, there are now many particles, right? Most of the particles in our visible universe, I think they exhibit some degree of entanglement, sir. Whether the entanglement in these objects or reason for the entanglement in universe, sir?
No, I don't know whether entanglement in universe is something which is an experimentally or theoretically strongly supported yet, right? When we look at it, no, that is what people call entanglement itself becomes very questionable at that point, because now we are only looking at entanglement which are measurable, observable, and theoretically, when we say it means a mathematically acceptable way. One can frame it. So in universe, we don't see a strong entanglement between various things, right? When we say, I don't know, when you say universe, are you talking about galaxies being entangled? Are you talking about some clusters being entangled? And people don't have any observations to look at it and look at and verify those things. It's all just like sci-fi interpretations of the way entanglement has been perceived.
And one more thing, sir, in the case of electrons, during entanglement, how long they entangle, sir? What's the lifetime?
That's actually a good question also, because that is very important here, right? When we say quantum computers, when people are building or when you are looking at the coherence time, what we call, are very, very small, which means the system that remain quantum mechanical, they have quantum degrees of freedom, is very small. Currently, the world's best quantum computers, where people do try to entangle some spin degrees of freedom and do computation, are in microseconds. They don't remain entangled even for microseconds, right? So they are so small. So all that process, all that operations you do in the nanoseconds scales, or within microseconds you finish. And that is biggest hurdle now to scale and build a real large scale quantum computer, right? It's not that it's just an engineering problem. It's a scientific problem as well, because controlling coherence or the effect of noise and destruction of entanglement is very difficult. So they are only lasting for microseconds. Why photon? They gave experiments, and why we can talk about photons? Because photon don't interact and they travel very fast. Even if I'm talking about traveling to thousands of kilometers, they are traveling in less than in a very short time, right? So, which means that they can remain entangled. Others, they don't remain entangled. That is a major issue here. Right? How long can they remain entangled? That is in microseconds, except photons. The rest of the things are currently it's all in the microseconds. All that people have measured, all that people have looked into. Even when we looked at these chemical complexes, they will entangle for a very short time, and they will again be disentangled. And there will be somewhere, entanglement happens in the dynamics, and again they disentangle.
So in that case, how one can predict the entanglement, sir? What are all the measurement methods available?
Yeah, okay. Yeah, like I mentioned now, what we that is, since it was good bit mathematical detail, I didn't go in specific, but I did say the correlation measurement, right? So
Yes.
what we do is that if you think there are two entangled
Okay.
systems, and then you try to have some different configurations of measurement output from both of them, and if they were not entangled, we should expect something. But if they are entangled, then we know that the result will be something different. So that is one way. And there is more other standard ways which we do in quantum information computing, is that we reconstruct a density matrix itself of many body systems. So I don't know whether you have studied density matrix representation in quantum theory. Once we get that, calculating correlations becomes very easier. Mathematically, we can calculate and then say whether they are entangled or not. So there are other entanglement witness measures. There are more than one different ways of measuring entanglement these days. So, but they are all based on measurement output, because we have to make measurement, we have to collapse. Because we have to make measurement and collapse, we use different bases. For example, if it is photon, I take some set of measurement using horizontal vertical polarization. Some set of measurements I can take using right and left circular polarization. I can use filters and then get those measurements, right? When I take these different orientations of filters, that's what Allen aspect did, right? You rotate the orientations, and then you measure. If you are rotating them, they should result in some kind of correlations if they have entanglement. So there are different ways people measure, and they're fine-tuning it to get the best measurement techniques.
Thank you, sir.
Do you use any trapping techniques to trap that one, or how do you?
Photons, we don't need to trap anything. You just send, we detect them passing through. But when people are doing with, people have done with atoms also. Atom entanglement between two atoms in optical lattices, where they're trapped. Atoms are trapped in an optical lattice using highly multi-dimensional configured laser beams. And then they engineer the interactions between one atom and another in different lattices, and they are entangled. So even ion trap is the current. When I mentioned microsecond coherence time, it's ion trap system till date. So they have the good coherence time to keep it entangled. So they also trap ions in different spatial distance, and then they make them interact, and then they generate entangled state between them. Depending on the systems. Photon you don't trap, you can trap, but you can trap atoms and ions. I think there is one more. Okay, that is the question which was asked. How can confirm that the quantum entanglement is because?
The limitation is because of the electronics or the instrumentation, or what is the limitation for all these experiments?
No, experiments, I don't see is largely electronics. Of course, there is the limitation.
When you want to go for a measurement, basically electronics comes in, am I right? Like you cannot think beyond.
So electronics, people are kind of resolved picoseconds been there. One of the things is the detectors also, right? Because we have to look at the correlations, detector efficiencies. We have to measure single photons at a very small time intervals. So currently, if there is a temperature, detectors also get disturbed, and it can register noise. The moment it registers noise, you are not getting exact number of photons which are detected. So detectors today we use in our lab are only like 65% efficient, right? So that's each detector costs some 10 lakhs for that. And people have used cryogenic systems to keep those detectors, and those like 1.3, 1.4 crores to get some 95% efficient detection capacity. That is one of the issues. The next is like how you engineer photon dynamics. Like if you can take it integrated, that will be easier. Theoretically, or like in a sense, science-wise itself, environment and the quantum system interactions is very strong. And how you isolate environment from a quantum system itself is a challenge. And people are working on it for years. So yeah, it is both engineering and science problem. That's what I mentioned. Like next 20 to 30 years, I think it is a huge. There will be a big progress in all the directions, irrespective of technology advancement, but science is going to advance. In fact, now the way one have control over photons and then handle them. People are looking at even applications towards biomedical or where you can only send entangled photons, which means a small number of photons, and some improvisations can happen to current technology applications.
So if no further questions, and we will thank again and Professor Chandru for giving a very extensive and elaborate presentation, starting from the foundation and till to the forefront of this cutting edge technology. And you can also contact him and you can visit his laboratory, I think, in Indian Substance.
Sure. Yeah, you can inform us in advance and we'll be happy to.
Okay.
In fact, we are seriously considering using your observatory for some entangled photon experiments because
you are most welcome, and we can have a MOU, and I welcome you to Kodai.
I think we are looking at in fact, we did have some discussions with the DRDO, and they were also very keen.
And it's a very nice place. Kodai, always you are most welcome to Kodaikanal.
No, I think, having entangled photons exchange between your stations and then measuring them will give some boost of going out of lab, because doing things in laboratory is good, but then going out of laboratory and doing measurements will have some implications.
Thank you so much. On behalf of all the participants and many people, they have come from the many directions and many locations. Thank you once again, Professor Chandru. Thank you again.
Thank you very much. Thanks to all of you. And it was good talking to you. Bye. Okay. Thanks.
Okay, I'll stop here. Thank you.